So in this problem, the gross domestic product in billions of dollars can be approximated by this function P of t, where t is the number of years since 1960. Okay, so we're going to start by finding the derivative of P of t, and then we'll explain what it means at a point. Okay, so before I find this derivative, actually, it would be easier to simplify. If I find the derivative like this, the derivative of 568 is 0, but then I'd have to use the product rule here because t is my first factor, and then this is my second factor. So if you don't want to use the product rule, then you would need to distribute that out before differentiating. So that's what I'm going to do. So t times t to the 0.6, we add those exponents to get t to the 1.6, and then minus 108t. Okay, so then p prime, I'm going to differentiate this. The derivative of 568 is 0. Then we have 37, and then I need to bring the 1.6 down. Let's see what 37 times 1.6 is. I get 59.2 for 37 times 1.6. So 59.2. T to the power of 1.6 minus 1.6. And the derivative of negative 108t is negative 108. It's the coefficient of t. Okay, that's p prime of t. Now we want to find p prime of 44. And I'm going to go ahead and do this in here as well. Okay, so we got p prime of 44. So we're going to plug 44 in for t. Okay, so there's my calculation for p prime of 44. So I get 465, and I need to see how many decimals. Round to the nearest tenth. So just rounded to one decimal would be 465.3. Okay, so what does it mean? So the derivative tells you the instantaneous rate of change of a function at a certain point in time. So this is telling us that when t is 44, so 44 years after 1960, that would be in 2004, the gross domestic product was, well, its derivative is positive, therefore the gross domestic product is increasing because the rate of change is positive. If the rate of change is negative, then your quantity is decreasing. So it's increasing by about $465.3 billion per year. That's how much it's increasing by every year, at least in the year 2004.